US square or H square, I suppose. I don't- Yeah, H square. Are you guys aware about this fact?
Yes, sir.
Yes, sir.
So this is nothing but central difference game. See, what do we mean by central difference is if I want to evaluate, okay, sorry, it is xi minus 1, sorry. So if this is my some real line, say this is my point x of I minus 1, this is my point some xi, this is x of I plus 1. So if you see this one, u prime of xi, then it is depending upon xi plus 1 and xi minus 1. And you're taking the difference to evaluate the derivative at this point. Okay, so in order to get this notation u prime of x of I, so what do? You start with some u of xi plus 1 and you go like this u of xi plus h and apply Taylor series, right? So one thing you can do is u of xi plus h times u prime of xi plus some remainder term. I am not concerned. For the timing, I am just making you explain for u prime of xi. Okay. And similarly, u of xi minus 1 can be written like this. U of xi minus h times u prime of xi plus r, right? So if I write from here, what will I get? U prime of xi is equal to u of xi plus 1 minus u of xi upon h plus order of h. So if you see this, it is known as forward difference. So it is known as forward difference scheme. Similarly, u prime of xi when it is equal to u of xi minus u of x of I minus 1 upon h plus order of h, then it is known as backward difference. And u prime of xi u prime of xi equal u of xi plus 1 minus u of xi minus 1 upon 2h plus order of h square, then it is central difference scheme. So haven't these three things discussed in the class?
Difference.
Hello, sorry for the trouble. So was it discussed in the class? These three things?
Sir, only central difference करवाया.
Okay, probably that's why she might have asked the central difference. So these are the three things. Okay, so these are clear by name probably because it is termed as forward difference because when we are calculating u prime here, we want our approximate solution to be at next point also, right? That we should be aware about u of xi plus 1 already in order to find u prime xi, right? And it is known as backward difference because if you want to calculate the derivative at xi, you are just depending upon xi minus 1. That means the one that is just before xi and then the central difference scheme. Okay, where you are depending upon the values of the approximate solution u at a inferior at a node which is before your exact node, say xi. So you are calculating at u of xi minus 1, as well as you want to know the value of the approximate solution at the next node, that is u of xi plus 1. Okay. So for the double derivative u double prime xi, what should be the approximation for the central difference scheme?
U of x plus h.
So u of x plus h is xi plus h, you mean, right? Because we
Yes.
want to calculate at xi.
Yes, sir.
So u of xi plus h, which is nothing but u of xi plus 1, right? Then
U of xi minus 1
plus u of xi minus 1 and
minus 2u xi
right,
divided by h square.
and this is of order
H square.
right h. Okay. So suppose we start with this. So suppose that this is my domain 0, this is my domain which is given 0 comma 1. So let it be x naught, then x1, then x2, and so on, x of n minus 1 and xn. Okay. So suppose we are dealing with this. So one thing which we have with us is u of x naught, which is u of 0, which is given to be equal to 0, right? So this is your equation number 1, right? Is this
Yes.
fine?
Yes, sir.
Now we have to use our given condition, that is minus u double prime is equal to f, right? So we can't find minus u double prime at x naught for sure, because we don't know u at x of minus 1 something, right? We can't do this, right? We can't find u double prime of x naught by our approximation, because from here we want to know it for u of x1, u of x0, and something u of x minus 1, right?
Yes.
So what will we do? We will find u double prime of x1. It will be u of x2 minus 2 times u of x1 plus u of x0 upon h square. It is given equal to f of x1, right? Similarly, we can find up to u double prime of x of n minus 1, which will be equal to u of xn minus 2 times u of x of n minus 1 plus u of x of n minus 2 upon h square is equal to minus f of xn minus 1, right? So if you see, we have something n minus 1 equations here and one equation here, total n equation. But we want to solve it for u x naught up to u xn. So we want n plus 1 equations, right? What are our degrees of freedom? We want to know u of x naught, u of x1, and up to u of xn, that is n plus 1 points. But till now we have only n points. Okay. So what should we do? If you see, we have one more boundary condition, that is u prime at 1 is equal to 0, right? So that is u prime evaluated at xn is equal to 0, right? But we are dealing with such type of equation where we are having u naught, ux1, ux2, something of this sort. So it is in u prime. So we have to approximate this also, right? Am I making sense here?
Yes, sir.
So if I apply central difference scheme here also at u prime of xn, so if you see the formula, but it should be u of x of n plus 1 minus ux of n minus 1 upon 2h. This is equal to u prime xn, right?
Yes, sir.
But again, we have only till xn. If you see, we have x naught up to xn. Our xn was 1. That was our domain. It was a restriction of our domain that we have to be in between 0 and 1. Right? So what we will do, we will give it a new node x of n plus 1. So it is an imaginary node which is not existing in our domain, but we will give this node for the time being. Are you getting my point? That this x of n plus 1 is not existing in our domain. Because if I say it is 0, it is 1 by n, it is 2 by n, 2 by n, then it is n minus 1 by n, it is n by n which is 1, then it will be some n plus 1 by n, right? But our domain was just omega was 0 comma 1. So what we will do here, add an imaginary node x of n plus 1 in the domain. Okay, because you see you are just shrinking your variable h, right? You are increasing your n. Then if for the time being, suppose this is your domain, it is 0 and say it is 1, suppose n is equal to 1, then it is x naught is 0, x1 is 1, then x2 which is x of n plus 1, it will be 2. If you take n is equal to 2, then you have x naught to be 0, 0, x1 to be 1 upon 2, x2 will be 1, and your this imaginary node x of n plus 1, x of 3, this is equal to 3 upon 2. And so on, suppose for the time being, say we take n is equal to 10. So x naught is 0, xi will be I upon 10, 1 less than equal to I less than equal to 10, and x of n plus 1, which is x of 11, it will be equal to 1.1. So your imaginary node is getting very, very close to your domain, right? So as n goes to infinity, it will not matter much. Are you getting my point? What
Yes.
I'm saying is initially our domain is just having 0, comma 1. So and we were dividing our domain into n equal subintervals. To divide it into n equal subintervals, we need n plus 1 degrees of freedom, you can say, hence n plus 1 equations. But we were not getting that. So what we did, we added an imaginary node, which for large n is sufficiently close to our endpoint. So now if I start with this term, this is my x naught, which is 0, then x1, and then up to x of n minus 1, xn, which is equal to 1, and some, let me take this main node with some new pen. This is x of n plus 1, imaginary node. So if we go like this, then what we have, again, u of x naught is equal to 0, equation number 1. Then u of x2 minus 2 times u of x1 plus u of x naught is equal to minus f of x1 dot h square, equation number 2. Similarly, we can go up to u of x, say n minus 1 initially, minus 2 times. So let me do like this. At max, we were going till u of xn minus 1, right? If you see here, we were going till u of x, u double prime x of n minus 1. So it is nothing but u of xn minus 2 times u of xn minus 1 plus u of xn minus 2 upon h square is equal to minus f of x of n minus 1. But now you can also find u double prime xn because you are already taking your imaginary node with you. So it will be u of xn plus 1 u of xn plus 1 minus 2 times u of xn plus u of xn minus 1 upon h square is equal to minus f of xn. So these are your n equations. This is one more equation, and also our another boundary condition, which says u of xn plus 1 minus u of xn minus 1 upon h, sorry, 2h, which is u prime of xn, it is also equal to 0. That is u of xn plus 1 minus u of xn minus 1 is equal to 0. So this is your equation number n plus 2, n plus 2 equation. So now things are simpler, right? We have n plus 2 variables with us from x naught to xn plus 1, right? And we have n plus 2 equations. Now we can find a matrix Ax is equal to B, A of u is equal to B, where A will be what? It will be 1, 0, and so on 0. Then for this equation, it will be 1, minus 2, 1, 0, and so on 0. Then for the next one, it is 0, 1, minus 2, 1, and so on 0, 0, 0. And we will go like this. So what will we have in the end? It will be for this equation. So we will have 1, minus 2, 1 here. And we have to do like this. U of x naught, u of x1, and so on u of xn, u of xn plus 1. It is my u. And if you see, we have this, we have to also import this condition also. So 0, 0, 0, and so on. U of xn plus 1, we need 0. We need minus 1 here and 0 here. Is this matrix A fine? See, this is the crux of this question. If it is not clear, please ask. I can repeat it again. If any step is not clear, please ask. Is this matrix clear to you?
Yes, sir.
Yes, sir.
Okay. So is the equation, so what we will do, we have our matrix B will be as 0 minus f of x1, right? Minus f of x2 and so on minus f of xn and then 0. So now we can do this. U is equal to A inverse B. We can solve this, and after getting all the nodes u node ux node to ux1, we can get it from here, right? So this is what the question asked you to do, that we have to implement a central difference scheme, sorry. Shall we proceed to next question?
Yes, sir.
So were you able to do question number 2?
Yes, sir.
So can you
Yes.
tell me what is the value of alpha for A and alpha for B?
So A for A alpha equal to minus 1 by 3 and for B equal to plus 1 by 3.
Right. And for C we have to do all those elimination part, right?
Yes, sir.
That alpha shouldn't be equal to plus minus 1 by 3, then we will have a unique solution, and then we can do all those Gaussian elimination part, that echelon form, right? You guys are in M.sc, so I think that you must be aware about these echelon forms, row reduced echelon forms, have all these notations, right?
Yes, sir.
Okay. So shall we proceed to question number 3?
Yes, sir.
Is it doable? Forget about question number 3A part. First of all, consider yourself to B part. Can you do question number 3 part B? Can you form this 2 by 2
Yes,
equation
sir.
to in? Can you transform this 2 by 2 equation into 4 by 4 equation? See, one thing you can solve it by this, right? A is equal to 1 minus 2 iota, 3 plus 2 iota, 2 plus iota, 4 plus 3 iota, and then z is equal to z1, z2, and say b is equal to this 5 plus 2 iota and 4 minus iota. So you will do az is equal to b and z is equal to a inverse b. This is one way. But can you transform this system of equation into 4 star 4 matrix and solve it as a system of linear equation in real time, real variables you can say, or coefficients. That is what question number 3A part is asking you. If you do it, if you can do it for part B, then part A will be trivial. So can you transform this system of equation into a 4 by 4 matrix?
No, sir.
Okay, let us do this. So we have equations as 1 minus 2 iota into z1 plus 3 plus 2 iota into z2 is equal to 5 plus 2 iota and 2 plus iota into z1 plus 4 plus 3 iota into z2 is equal to 4 minus iota. Okay, so what we will do, right? Z1 is equal to a1 plus iota b1 and z2 is equal to a2 plus iota b2 and substitute it here. So what we will get 1 minus 2 iota a1 plus iota b1 plus 3 plus 2 iota a2 plus iota b2 is equal to 5 plus 2 iota. Let us solve this. Then we will get a1 and plus 2 times b1 plus iota common b1 minus 2 times a1 plus 3a2 minus 2 times b2 plus iota common 3 times b2 plus 2 times a2 is equal to 5 plus 2 iota, which is nothing but a1 plus 2b1 plus 3a2 minus 2b2 has to be equal to 5 and minus 2a1 plus b1 plus 2a2 minus 3b2 is equal to 2. Is it understandable?
Yes, sir.
Comparing real and imaginary part. So from equation number 1, we have made two equations. So similarly, from equation number 2, we can make two more equations.
Yes, sir.
So now is it doable?
Yes, sir.
Yes.
Does question number 3 make sense now?
Only B part, sir.
So that is what you have to do with A also. So if I say A is some matrix which is say like this, A1 plus iota B1 say, then A2, okay, let me be more precise here, A11 plus iota B11, A12, it is yeah, A1, A12 plus iota B12 and so on, A1n plus iota B1n, and similarly here an1 plus iota bn1, an2 plus iota bn2, and so on, ann plus iota bnn. Into you will have here said a1 plus iota b1, a2 plus iota b2, and so on, an plus iota ben. It is your matrix A, this is your vector x, and for B, it will be something of this sort. Again, let me make it some like this, C2 plus iota D2, and so on, Cn plus iota Dn. Now we have to do the same thing here. We have to multiply and add. So this equation, say the first equation, a11 plus iota b11 into we have a1 plus iota b1 plus a12 plus iota b12 into a2 plus iota b2 plus and so on, a1n plus iota b1n into an plus iota bn is equal to c1 plus iota d1. So in order to solve this, you will what do you have? A11 A1 minus B11 B1 plus A12 A2 minus B12 B2 plus and so on, A1n AN minus B1n Bn is equal to C1, and then A11 B1 plus B11 A1 and so on, A1n Bn plus B1n AN is equal to D1. So first equation is giving us again two equations, and then we can solve. Is this making sense now? Question 3 part A. You can also write it in compact form also. If I want to write it in a compact form, it will be summation A1 I dot AI minus B1I dot BI running from 1 to n is equal to C1 and summation I running from 1 to n A1I BI minus B1 sorry plus B1I AI is equal to D1. So now you can make a vector say X to be of this form A1 B1 A2 B2 and so on up to A and Bn. Anything of your wish, or you can also write it like this A1 A2 and so on An B1 B2 and so on Bn. But correspondingly you have to change your A, suitable A. Is this making sense now?
Sir,
Yes, sir.
Okay, I heard one yes sir and one just sir. So was there a question?
sir,
Yes.
सर इसका सॉल्यूशन था, उसमें ये लिखा हुआ था कि मैट्रिक्स ए को रियल और इमेजिनरी में डिकम्पोज किया हुआ था, लाइक मैट्रिक्स ए को लिख दिया रियल पार्ट ऑफ ए एंड इमेजिनरी पार्ट ऑफ ए एंड देन वेरिएबल्स को लिख दिया.
Then we will do some same for the variable and we will multiply, right?
Yes sir.
So but don't you think that it is also doing the same thing? See, you have to transform it into a 2n matrix, right? In which all the entries should be real. What you are saying is you are decomposing A as A1 plus iota times A2, where A1 and A2 are real systems. But you have to multiply these things with Z, right? Where Z is a complex system. So you are not solving it for the real system completely there. Is this what you are talking about, or you are saying something else?
Yes sir.
I didn't get you. See, if we go with this stuff, then but what will be the problem? A1 Z1 some Z plus iota times A2 Z is equal to B, something B, right? So you can't do the inverse thing and something. What you will do, you will do it like this. Say B1 plus say iota B2. Even if you go like this, then also it doesn't make sense, right? Because you can't say this matrix is completely real. You can't say, because you have a complex entries here. So you can't really say A1Z should be B1 and A2Z is equal to B2. This is completely wrong. You can't say this, right? Is this what you were suggesting, or am I mistaking something?
Sir, for example, A is a 2 cross 2 matrix,
Okay,
complex
take
matrix.
to be take whichever whatever is given us here. Okay, 1 minus 2 iota, 3 plus 2 iota, 2 plus iota, and then 4 plus 3 iota, right? This is our thing.
Yes sir.
Okay, then
देन सर बुक में लिखा हुआ था सॉल्यूशन, इसमें ए को डिकम्पोज, ए को लिखा है ए इक्वल टू
right, say
1
right, 3
-2.
minus 2.
सर लाइक ये जो नहीं सर, ए को 4 क्रॉस 4 मैट्रिक्स लिखा है.
Okay, okay, 1 3, then it will be minus 2 and it will be 2. Is it so?
सर +2 and -2.
Okay, so plus 2 and minus 2.
Yes, sir. Then second
Then
row.
what will be the? Okay, tell me what is second row.
2, 4.
2, 4.
Yes, sir. -1, -3.
Minus 1, minus 3. Okay, then third row.
Third rows are -2, 2, 1, 3,
And then fourth.
1, 3,
1, 3.
2, 4.
Okay. And then what is your Z?
Set is x1, x2, and y1, y2.
I1, Y2. Where probably you are writing your Z1 as X1 plus iota Y1 and Z2 as X2 plus iota Y2. Isn't it?
Yes, sir.
Okay. So let us see whether we can do it from here also. Whether you are getting the same matrix or not. If you are getting the same matrix, then things are fine, right?
Yes,
Because
sir.
you must know why we are getting such matrix, right?
Yes, sir.
Okay, let us do that. So what it is 1 minus 2 iota x1 plus iota y1 and then plus 3 plus 2 iota x2 plus iota y2, right? So if you solve this, you will get x1 and then plus 2 y1, then plus 3x2 and minus 2 y2, isn't it? So it will be equal to it is going to be equal to 5 plus 2 iota. And another equation will be minus 2x1 and plus y1 plus 2x2 plus 3y2. So it will be equal to 5, it will be equal to 2. Similarly, if I solve this, 2 plus iota x1 plus iota y1 plus 4 plus 3 iota x2 plus iota y2, it is given to be 4 minus iota. So let us write this also, 2x1 then minus y1 plus 4x2 minus 3y2 is equal to 4 and x1 plus 2y1 plus 3x2 plus 4y2 into iota again is equal to minus iota. So basically let me write it equal to minus 1. So if I want to make it as a matrix of x1, x2, y1, y2, so it will be nothing but 1, 2, 3 minus 2. Okay, sorry. It will be 1, 3, then 2 minus 2. Let us write this first. 2, 4 minus 1 minus 3. Now let us write this. It is my first, it is my second. Let me make it third. Let me make it fourth. Minus 2, then 2, then 1, 3. And here it is 1, 3, 2, 4. It will be equal to 5, 4, 2 minus 1. So I think your book is suggesting the same matrix.
सर एग्जाम में अगर ये क्वेश्चन आए तो डायरेक्टली रिजल्ट यूज कर सकते हैं कि बुक वाला डायरेक्टली
See,
ऐसे मत
book में I don't know but result is given. I am telling you the process how to do it. If you are quite able to make this matrix directly, then it is very good. You can do that.
ओके सर
But you might not get the same example again and again, right? In the exam, you might get a 3 cross 3 matrix. That is why I was telling you the way, how we are doing the stuff.
ओके सर
So is it understandable? If you are quite fine how to write this matrix directly, that is completely understandable. That it will be correct.
सर जो फर्स्ट
But you
2x2 मैट्रिक्स लिखी है ना 4x4 में, ये सर ए का रियल पार्ट है, और सेकंड है ये माइनस ए का इमेजिनरी पार्ट, और थर्ड 2x2 मैट्रिक्स है, कॉलम है, इसमें वापस वो ए का इमेजिनरी पार्ट है, और फोर्थ लिखा है वो ए का रियल पार्ट। लाइक सर हम कॉम्प्लेक्स नंबर x प्लस आयोटा वाई को मैट्रिक्स फॉर्म में x माइनस वाई वाई एक्स लिखते हैं, वैसे लिखे।
okay? So what you are saying is some completely you are just something you are just what should I say? Integrating all these facts into one simple line, and that is completely correct. Probably I was going with the somehow a longer procedure, but what you are saying is completely correct. I'm not denying that. So if you want to write it, you can just make it like this also: a1 plus iota a2, and then make it z1 plus iota z2 also. Then you can think of something like this: a1 z1 minus a2 z2 plus iota times a1 z2 plus a2 z1, right? And if you now write it z1 vector as z11 z12 and z21 z22, then you will get what you are saying here, that only a1 directly and minus of a2. That's what you are saying, right?
यस सर।
Yeah, that is completely correct. So I hadn't thought of it in my first instance, but that is completely correct. If you want to go like this, that is completely correct. So are we clear with question number 3?
यस सर।
Okay, what about question number 4? Question number 4 and 5 are completely similar. Were you able to get this number of multiplications?
सर फोर्थ क्वेश्चन में ए एन क्रॉस एन मैट्रिक्स है, तो सर एन
Right.
नॉट इक्वल एम होगा, तो फिर वेरिएबल्स एम कैसे लेंगे, मल्टीप्लाई कैसे होगा, ए एक्स सेंस कैसे बनेगा?
X is also n cross 1 vector. Here A is an n cross n matrix and X is an n cross 1 vector. So basically, if you want to see it, will be something of n cross m vector. If you really want to see it, that is how it is working. But it is asking you, you have fixed an A, and for each B, you want to get some X. That is the question demanding. So now AX is making sense to you probably. Sorry, let me frame it more permanently. So but it says is A is your n cross n matrix, and then your X is n cross 1 vector, but m times. So it is something of this sort: x1 vector, it is an n cross 1 vector, then x2, and then xm. So something of this sort. Okay, let us make it some sort of matrix. Say A is equal to A1, A2, A3, A4. Okay, and say for the timing m is equal to 2. Okay, and take B1 as B11 vector, B12, and say B2 is equal to B21, B22. So what we want as some x1, which is say x11, x12, and x2, which will be something x21, x22, such that a of x1 is equal to b1 and a of x2 is equal to b2. That's what the question is asking to you.
Okay, sir, now clear.
right? So if you go with A to be an n cross n matrix for the timing, and if I want my x to be some n cross m matrix, then Ax will be my n cross m matrix, which is nothing but this B1, B2, and so on up to Bm. This vector n cross m vector each, right? But the question is asking you, instead of solving this Ax is equal A of x1 is equal to B1 and then A of x2 is equal to B2, what you do is you make a single augmented matrix and do the calculations in one go only. Instead of solving this as like this AB1, AB2, you can also solve this A of B1, B2, so that you need to do less number of operations. Because if you do some operations here, and you will have to do the similar type of operations here also, right, in order to make A to be say lower triangular or upper triangular matrix. So why not we do it only once? So is the question clear? But is the question is asking you?
Yes, sir.
Okay, so do you want me to do this calculation, that if I want to go through the Gauss elimination part, say if I want to solve this matrix B1, B2, and so on Bm, say this using Gauss elimination, then we need to apply multiplication or division. We count as one unit. How many times? N cube upon 3 plus mn square minus n upon 3 times. So see, this is not the exact figure. Say you might have zero somewhere. You might not need to do the calculations for each pivot entry. So this is the maximum thing. If something that, okay, so suppose this is your case A1, A2, A3, and suppose this is A1, A4, A5, and A1, A6, A7. Suppose this is the case. So you don't need to multiply, you just need to subtract this R2 minus R1, A4 minus A2, A5 minus A3, A6 minus A2, A7 minus A3, right? But this formula is counting like this, that we are doing A1, A2, A3. We are doing A1 minus this entry A1 upon, sorry, this entry A1 upon, okay, let me write it as A12 for the time being. Sorry, A21 upon A11 into A11. And here it is doing like this. So this formula is working in this manner. Although in some metrics we might not need to do this multiplication and all, but this formula is working in this manner, that we are doing multiplication at each step. Okay, did I made confused you with the problem, or the problem is getting clear? Okay, let's do one thing. Take A to be n cross n, and for the time being, take m is equal to 1 only, and see whether you are getting these number of operations or not. Multiplication operation. Or you want me to do this? Say yes or no. You want me to do this calculation for question number 4, or you can do it yourself? And
करा दीजिए sir.
yeah, I didn't get you.
Do it sir.
Hello. Please repeat.
Solve it sir.
करवा दूं?
Yes sir.
Okay. Okay. The thing is, you guys are not quite clearly audible to me. Am I audible to you guys properly, by the way?
Yes. Yes sir.
Okay. Great. So let us do it for m is equal to 1 for the time being. Okay. So say we have this matrix A11, A12, A1n, A21, A22, A2n, AN1, AN2, and so on. And we have a straight line to form an augmented matrix B1, B2, and so on Bn. Right? So, what is our first thing when we go through the Gauss elimination method? So, what do we do? Assume that all these things are pivots, so we don't need to do the permutation stuff. So, for the time being, we assume that everything is very clear to us that the pivot are there. We don't need to do any type of permutation stuff. Okay, so for example, when ma'am have done something of this sort in the class, she must have assumed for the time being say A11 to be non-zero, right? And then you must, okay, in doing the LU decomposition, she must have assumed that A11 to be non-zero, and then you must have got some new matrix where these entries are A22 delta and something. Then she must have assumed that, okay, assume A22 delta is non-zero and so on, right? What is our primary
Yes,
target? We
sir.
want to make it zero, right? This entry to be zero, first of all. Right? So I want this entry to be zero, first of all. So what do I do? R2 minus A21 upon A11. So this is just one real number. So it will be counted just one. You will not count it as, okay, we are doing A21 times R1 and then we are dividing by A11. No. We are multiplying R1 by this entry, A21 by A11. Okay. So this is one multiplication. Okay. Is it clear?
Yes, sir.
Okay. So see, you have to multiply this whole row by A21 by A11 and subtract R2 minus R1. So you have n plus 1 entries, right? You have to multiply A11 by A21 by A11. Then you have to multiply A12 by A21 by A11 and so on up to A1n. So what do we need to do? This thing. A11, A11, and so on. We have to compute all of these terms and B1 into A21 by A11, right? In order to make this zero, we have to calculate these terms, isn't it?
Yes, sir.
So in order to make this zero, we are doing n plus 1 multiplications as of now, right? Similarly, in order to make this entry, A31 entry, to be equal to 0, we will again need n plus 1 multiplication operation. But we will do R3 minus A31 upon A11 time R1, right? So basically, we again have to find these type of thing. A3 1 by A11, A1n, A3 1 by A11, and then B1, A3 1 by A11, right? In order to make this entry to be 0, right or not? Is it making sense that in order to make third row first entry to be 0, we again need to do n plus 1 times multiplication?
Yes, sir.
So basically, how many rows do we have here? N minus 1 rows, right? So we have to do n minus 1 times n plus 1. These many operations just to make the first column to be 0. These many operations to make ai1 to be 0 for all I greater than 1, right?
Yes, sir.
Okay. Now we our matrix will look like something of this sort: a11, a12, and so on, a1n. But now we have some a22 tilde, it will be 0, a32 tilde, an2 tilde, a23 tilde, a2n tilde, a33, a3n tilde, an3, and so on, an3. And here b1, but b2 tilde, b3 tilde, and so on, bn tilde, right? After applying these many operations, our matrix will transform to something like this. Fine.
Yes, sir. Fine.
So now what do we want? We want to make this column to be 0. So basically, what do we need to do? First of all, we will multiply this thing a32 tilde by a22 tilde. We have to multiply again this term and so on. A21 tilde, right? And subtract. Basically, what are we doing? R3 goes to R3 minus a32 tilde upon a22 tilde into R2, right? In order to make this entry to be 0.
Yes, sir.
So basically, how many times, in order to make this entry to be 0, we are doing n times multiplications, right? We are using n time multiplication operator because we are just left with n entries now. So basically, n. But for a42 tilde also, we will need n entries, n times multiplication, and so on up to a and 2 tilde also. So basically, n into n minus 2 because these are n minus 2 rows, right?
Yes, sir.
Okay, then what do we have? How many operations we have done till now? N minus 1 into n minus 2. Sorry, n minus 1 into n plus 1, n into n minus 2, and so on. At one stage of time, we will have 1 into 3. Right? If we go in this manner, that the next term will be what? We will have n minus 1 into n minus 3, right? So continuing in this manner, we will have 1 into 3. And we will get an upper triangular matrix. isn't it?
Yes.
But see, our work is not over yet. We have just bent, we have just transformed our matrix to an upper triangular matrix. We haven't got the solution. And they are asking us to get the solution by Gauss elimination. So now we have to do the backward substitution. And in that case also we will need some sort of multiplication operator. See, if I say this is what we have, a11, a1n, 0, a22, a2n, and so on, an minus 1, an minus 1, n minus 1, an minus 1, n, and then an n. So this will be my matrix, right? And this will be my 0, upper triangular matrix. So what you will need to do in order to find x1, x2, and up to xn, if it is say equal to b1, b2, and so on up to bn. So you will have xn to be 1 upon ann into bn. So basically, one time multiplication operator is used, right? Also, an minus 1 and minus 1 times x of n minus 1 plus this term an minus 1 n into xn. Xn you have already found it out. It is equal to bn minus 1, right? So one multiplication here. So x of n minus 1 will be 1 upon an minus 1 n minus 1 b of n minus 1 minus this entry. So one multiplication here. This is our star. One multiplication and one multiplication here. This is our star. So total two multiplication. Similarly, in order to find x of n minus 2, we will need 3 times multiplication operator, right? Is it making sense? For xn, we are using 1 times multiplication operator. For x of n minus 1, we are using 2 times multiplication operator. For xn minus 2, we will use 3 times multiplication operator, right? And similarly, for x of n minus 1, which is nothing but x1, we will need n times multiplication operator, right? So if we sum it up, so how many times we have used it? N into n minus 1 plus n into n minus 2 plus n minus 1 n minus 3 plus and so on up to 1 comma 3 plus 1 plus 2 plus 3 plus and so on up to n multiplication operators. Does this make sense now? In order to solve using Gauss elimination, we will need these many multiplication operator. But for once, this doesn't seems to be quite solvable because we don't know n, right? So you can write it in this manner: I going from 1 to n, I minus 1 into I plus 1 plus summation I running from 1 to n I. This thing is nothing but this. This thing is nothing but this. And you can solve it now. I running from 1 to n I square minus 1 plus summation I running from 1 to n I. So it is nothing but summation I running from 1 to n I square minus summation I running from 1 to n times 1, which is nothing but n, plus summation I running from 1 to n times I. Now you know the formula for this, right? Sum of square of first n natural number. What is it?
n into n plus 1 into 2n plus 1 by 6.
Upon 6 minus n plus n into n plus 1 upon 2, right? So now just solve this. It is 6 n into n plus 1, 2n plus 1 from here, and minus 3 from here, minus 6n. If you solve this, you will get n into n plus 1 into n minus 1 into 2 minus 6n upon 6 on solving, n into n square minus 1 upon 3 minus n, which is nothing but n cube upon 3 minus n minus n square upon 3. Okay, I think I have done. Okay. Am I still audible? Because my Bluetooth just.
Yes.
Yes, sir.
So probably I have made some calculation mistake somewhere. It is 2n plus 1 minus 2. Can you figure it out for me, please? Till here it is perfectly fine, I'm sure, because till here we haven't done any calculation error. Okay, this is fine. It is n cube only because it will be from here. We want plus n square. So why we are getting some wrong answer here? Let us do this calculation again. N square plus n times 2n plus 1. This is what this comes out. Minus 6 times n plus 3 times n square plus 3n upon 6. This is what we have with us. So it is 2n cube plus n square plus 2n square, it is 3n square. Okay, right. We are
Yes,
making a mistake
yes,
here, right? It is 2n plus 1 plus 3, right?
Yes.
So it will be n plus 2. Okay. Now let us do the calculation again. Okay, we were doing it really good here. Sorry for the disturbance. Yeah, if we go like this, it is 2n cube plus n square plus 2n square, it is 3n square plus n 2n cube plus n square plus n square plus n minus 6n plus 3n square plus 3n upon 6. If you solve this, it is 2n cube plus 3n square plus 3n square, it is 6n square minus 2n upon 6, which is nothing but sorry for the disturbance. I think I need to end this class as of now. Just let us complete this last line. N cube My pen is also not working, but you can see that at least we have got what we desired, right? N cube upon 3. We are getting n cube upon 3 plus n square minus n upon 3. But this is what we desire, right?
Yes, sir.
Is this fine for m is equal to 1 at least?
Yes.
Sir.
Okay. Probably it might confuse you somewhere, but if you just try to write it step by step once, you will not get it in so much of trouble. Okay. So have you tried doing other questions by the way? That 6, 7, 8, 9, 10? Have these things that P transpose LU transformation or Chomsky factorization have been taught in the class?
No, sir.
Okay, probably she will teach them. Okay, let us end the meeting as of. Okay, tell me, is there any doubt till question number 4? And if you have understood question number 4, then question number 5 is quite trivial. Because there you have to do the Gauss-Jordan elimination instead of Gauss elimination. So instead of going to the upper triangle matrix, you have to make a diagonal matrix somewhere. So can you assume that question number 1 to 5 is clear?
Yes, sir.
Okay, please try doing rest of the problems. Okay, if these Chomsky factorization and LU factorization have not been taught in the class, so we will discuss assignment sheet 9 first of all in the next class. Probably by that time she might teach you these methods also, and if she doesn't, then I will teach you these methods. Okay. So before coming to the next class, please have a reading or solve assignment sheet 9. If these methods is not discussed in the class. Okay.
Okay, sir.
Okay, you guys can leave then.